All right, let's get started. Welcome to the third lecture of CS294-112. Today we're going to introduce some of the basic definitions and objectives behind reinforcement learning and discuss sort of a brief overview of a range of reinforcement learning algorithms. But first, again, a few logistical notes. So homework 1 milestones are due in about 1 week. Please be sure to check out homework 1, try to get everything set up. It's a good idea to try training some networks with TensorFlow if you run into trouble. There's some TA office hours this afternoon. There's some TA office hours Monday afternoon, Wednesday afternoon next week. So make sure you get the help that you need if you're having a little trouble there. Good idea to start early. And then next week on Friday, we'll have the review session led by Josh. And if you try homework 1, you try the milestone, you have a little bit of trouble, also a good idea to go to that review section. And don't be late with the milestone submission, please. Remember to start forming your final project groups. So we'll get some initial final project ideas. We have a document that we're preparing where we're listing some ideas for final projects. You can come up with your own. In fact, you're very strongly encouraged to come up with your own. But if you'd like some ideas, we'll have that for you in about a week or so once we're done filling that in. And we'll also put out the final project assignment also in a week or so, just so you know what's coming. So the milestones and the proposals and so on, they're on the course website, so they're not for a little while. I think you have almost a month for them, but good idea to start thinking now, forming project groups and so on. For homework 1, those of you that are enrolled in the class will have received an email from me with the Mujoko license. The email went to whatever email address you have in Cal Central. If the email address you have in Cal Central is not one that you have access to, then you didn't receive a Mujoko key. So you can contact the TAs or make a private message on Piazza. We'll email the key to you directly because we can only provide it to students who are actually enrolled. All right, so today's lecture. We're going to talk about the definition of Markov decision processes, which is one of the most fundamental mathematical formalisms in reinforcement learning. I'll provide a definition of the reinforcement learning problem, basically the objective that we're trying to optimize in reinforcement learning. Give a sort of a high-level overview of the anatomy of a reinforcement learning algorithm. And in fact, almost all of the algorithms that we'll learn about will follow the same sort of basic high-level structure, which I'll introduce today. And then a brief overview of the kind of types of RL algorithms we'll cover in this class. So most of the lecture will deal with definitions and problem statements, and we'll really dive into the particular details of the algorithms starting next week. But here I'll just give you a high-level overview so you sort of have a roadmap to know what's coming. So the goals for today's lecture will be to understand the definitions and the notation in reinforcement learning, to understand the underlying reinforcement learning objective, and to get a summary of the kind of algorithms we'll learn about, and an initial hint of their pros and cons, of their strengths and weaknesses. All right, so let's start with some definitions. Last lecture on Monday, we learned about what is a state, what is an observation, what's a policy, and so forth. And in particular, we saw this graphical model, and this is going to come up again in today's lecture, that describes how observations might influence actions in a partially observed policy, how the current state and the current action influence the next state, and how the future states are independent of past states conditioned on the present, which is called the Markov property. So this we learned about on Monday. Now, we talked about how we can train policies, pi, that give a distribution over actions conditioned on observations using data obtained from, for example, from a human demonstrator with supervised learning. And this is imitation learning. So imitation learning is how we can get policies for sequential decision making using example data. Today, we're going to talk about how we can do this without example data. So if we don't have data, we need some way to define the task. We covered this briefly at the end of Monday's lecture, but we need some kind of reward function, something that describes what is a good behavior versus what is a bad behavior. So which action is better or worse, or which state is better or worse, that's given by the reward function. and it tells us which states and actions are preferred. So in the driving case, if you don't have data, maybe what you might say is you have a high reward for happily driving on the road at the desired speed, and maybe you have a low reward for being in a state where you've collided with another car. And the crucial thing about the reward function is that it's not something that tells you how to act right now. It tells you what outcomes are desirable or undesirable. And the job of the reinforcement learning algorithm is to figure out which actions to take now so that future outcomes will be more desirable. This is sometimes referred to as the delayed reward problem. And this is a very kind of basic thing that reinforcement learning algorithms try to address. So if you're just driving down the road, you don't know necessarily which steering commands will result in a car accident 30 seconds from now, but you have to reason about that. You have to figure out what to do now because you'll only figure out that the outcome is bad later. So these things that we've defined, the state, the action, the reward function, and the transition probabilities, together they define what's called a Markov decision process. So let's talk about Markov decision processes. And before we do that, we'll go to something a little bit more basic. We'll talk about Markov chains. Well, first of all, who is this guy Markov? This is Andrei Markov. He's a Russian mathematician from the turn of the previous century who worked on stochastic processes. Markov chains are not themselves actually very directly related to reinforcement learning. They're just a formalism for reasoning about a particular kind of stochastic process. And they're defined by two things: a set of states, S, and a transition operator, T. The set of states, S, that's your state space. So any state you have is a member of the set S. And it can be either discrete or continuous. So it can be, for example, a categorical variable that tells you that you're in one of a set of discrete states, or it can be a vector of continuous numbers. And T is a transition operator, and T defines the probability of entering a new state given the current state. And the reason that we could call this a transition operator is because if your states are discrete, actually also if they're continuous, but especially if they're discrete, the transition operator is actually a linear operator. So to understand what this means, let's say that we have our discrete states and we put the probabilities of being in a particular state into a vector mu t comma I. So mu t is a vector and mu t comma I is the probability that you're in state I at time step t. So mu t is a vector that sums up to 1 that gives you the probability of being in a particular state at time t. Now, so this mu t is a vector of probabilities, and we're going to say that capital T here is a matrix where Tij is the probability of transitioning to state I, given that you're currently in state j. So it's just a matrix that if your state has dimensionality n, this is n by n. Then the probability of being in a particular state at time step t plus 1 can be obtained just by multiplying that matrix times the vector of probabilities at time t. So it's a linear operator. And that's awfully convenient for a lot of analysis, some of which we'll do later in today's lecture. If your states are continuous, that just means you have an infinitely large set of states. It's still a linear operator, it's just an infinitely large linear operator. And of course, we can draw the Markov chain as a graphical model. And unsurprisingly, this is what the graphical model looks like. And it already has that independent structure. So you can see that if you know S2, then S3 is independent of S1. And that's also reflected by this equation, because the probabilities at time step t plus 1 depend only on the transition operator, which is constant, and the probabilities at time step t. So this is the most basic structure that has the Markov property, this independent structure. If you hear about second order or third order Markov chains, that just means that it depends on the current step and the previous one or the one before that. In reinforcement learning, we typically deal only with first order Markov chains, although generalizations to higher order are also reasonably straightforward. Okay, does anybody have any questions about Markov chains? Okay. All right, so yeah, Markov property independent of st minus 1. All right, so now let's talk about Markov decision processes. This is an extension of Markov chains to a decision-making setting that was popularized by folks like Richard Bellman in the 1950s. And the Markov decision process is a generalization of a Markov chain that adds a few additional things in there. So there's still the state space S, just like before, but now there's also an action space. And the action space, just like the state space, can be either discrete or continuous. So it can be a categorical variable that indicates taking 1 out of n actions, or it can be a vector of real valued numbers, or it can actually be a combination of those two. So the corresponding graphical model now looks like this. Just like before, there's this backbone consisting of states, but now every transition is also influenced by an action. And the action can be chosen however you want. So there's still a transition operator T, but now this transition operator is three-dimensional. It's a tensor. because it describes the probability of entering a particular state given a particular current state in action. So now the way that I'm going to write this out as an operator is I'll define my mu the same way as before. Mu is the probability of being in a particular state. So mu t comma j is the probability that you're in state j at time step t. I'm going to have this psi, which is the probability of taking an action k at time step t. And for now, I don't care where this probability comes from. In practice, it would come from a policy, which is conditional. But for now, let's not worry about that. Let's just say this is my probability of taking an action. And my transition now has 3 dimensions. So t I j k is the probability of being in state I at time step t plus 1, given that you're in state j at time step t, and take action k at time step t. And now, just like before, we can write a linear equation that's linear in the transition operator to obtain the probability of the next states. And I just wrote it like this with the summation. You can, if you're very familiar with tensor notation, there's ways to write it out that are a little bit more compact. But this just, I think, makes it a little more clear that the probability at this should be t plus 1, by the way, that's a typo. The probability of being in state t plus 1, in state I at time t plus 1 is just obtained by multiplying together all these things. OK, so that's all kind of reasonably straightforward. There's one more thing in the Markov decision process that I haven't talked about yet in this definition, but we already know what it is, which is the reward. So the reward function is the last part here that we need to have, and that's just a function from the set of states and actions to real valued numbers. So we already introduced that, and that's the reward. So together, these things fully define a Markov decision process, which can be used to specify a reinforcement learning problem. There is one more generalization of this idea that we need in order to round out our set of definitions, and that's the partially observed Markov decision process. So the partially observed Markov decision process adds 2 additional things. It adds an observation space O and an emission operator E. So we have the state space S like before, we have the action space like before, and now we have an observation space. And just like the state space and action space, the observation space can be either discrete or continuous. It can basically be whatever you want, and you have your set of observations. So the corresponding graphical model is this one, which is very similar to what we saw before. For now, we're not dealing with policies. That's why this edge is missing. But if you have a policy, then you have an edge over there. For now, we're not talking about policies. We're just specifying the problem. So the state gives rise to the observation, and the state and action give rise to the next state. So we have the same kind of transition operator. It's still 3-dimensional. And now we have an emission probability that tells you how likely is a certain observation to occur at time step t, given a state at time step t. And again, we have the reward function. And the reward function, just like before, maps states and actions to real valued numbers. So the reward depends on the state, but your policy typically would only get the observation. So it has to figure out what's going on from that. OK. Does anybody have any questions about these definitions, about Markov decision processes or partially observed Markov decision processes? Yes?
Sorry, I guess I don't understand why partially observed one has the emission probability.
Right. So a concrete example of what this might be is if you remember the example with the cheetah and the gazelle from Monday, the observation might be something like the image that you see. So your camera observes some pixels, and the set O is the set of all possible images. It's actually a discrete set because your images are discretized. The state S is the configuration of the underlying physical system. So that might be like the position and velocity of the cheetah and the position and velocity of the gazelle. If those are the only things in your universe, then they basically determine the observation. The observation might still be stochastic. Maybe your camera is noisy, so there's still some probability here. Maybe your camera injects some like white noise. So that's why they're distinct. And the partially observed Markov decision process generalizes the regular Markov decision process. So you can trivially reduce it to a Markov decision process just by saying your observation is the state. And then you get back to the same thing. So the partially observed Markov decision process, or POMDP as it's sometimes pronounced, is the most general form of this problem. Yes, back there.
Why does the reward function have to map from the Cartesian, the state, and the action? Why can't it just map states to rewards or states to real values?
It can. So that's a special case of this. In general, actually, sometimes people write it even in an even more general way. Sometimes people say that the reward function is a function of the state, action, and next state. Which makes sense in some contexts. But the version where the reward function only depends on the state is just a special case of this. Yes?
How would you distinguish a POMDP from like an end-order Markov decision process? Like if you could say that a state could be like the entire history and the observation could be the current state, like would that be the, like could you formulate that as Could you formulate an
Right. We'll talk about this a little bit more, I think, when we talk about recurrent policies later. But yeah, basically the short version is that everything, like if you have some observation at a particular time step and you have a partially observed problem, everything you know about the world is sort of contained in the history of observations you've seen. So you can transform a PUMDP into an MDP by concatenating all of your observations into a history. It's not actually the same process, but you can actually show that you can't do your policy can't be any smarter than a policy that takes in the whole history, because that's basically all you know. Yeah. So that's one way to reduce a PUMDP into an MDP for the purpose of computing a policy. Yes?
Is there anything interesting about having the reward be probabilistic, or it's determined?
So this is going to kind of relate very closely to what is the objective of reinforcement learning. The reason that we typically don't consider probabilistic rewards is because, as I'll show on the next slide, we typically care about expectations of rewards. And if you have a reward that is some function of SNA plus noise, if you consider expectations under state distributions, they're also going to end up expectation of the noise. So you might as well just average out the noise first and use the expected rewards, and you'll actually get the same solution. This might get a little more delicate if you deal with things like risk-sensitive decision-making problems. And towards the very end of the course, we might have a guest lecture that actually talks about risk-sensitive decision-making. Any other questions? All right. So let's continue. Let's now introduce the goal of reinforcement learning, the basic objective that pretty much any reinforcement learning algorithm is trying to optimize either directly or indirectly. So we're going to have some kind of policy. And we won't actually always have policies represented by neural networks. Sometimes our policies will actually be implicit. They'll actually be a consequence of some other function, like a value function or a Q function that we'll learn about later. But for now, let's say that the policy is explicitly parameterized. So it's a neural net. It has parameters theta. We'll just deal with a fully observed case for now. So I'll just talk about regular Markov decision processes, but we'll revisit partially observed ones later. So for now, let's say it depends on the state. And its parameters theta are the weights of that neural network. And the state goes in, and the action comes out, and the action is sent to the environment. And then the state is also sent to the environment, and the environment uses its transition operator, which in general we assume that we don't know, to choose the next state. So this is kind of the cycle in a reinforcement learning problem. Your policy looks at the state, or at the observation, it outputs an action. The world looks at the state in action, outputs the next state, and it keeps going around like this. Now, this process gives rise to a distribution over state action sequences. So if you have a finite horizon task, and we'll talk about infinite horizon in a second as well, but if you have a finite horizon task, which means that you exist in the world for capital T time steps, then you can say that your probability over trajectories over sequences of S's and A's is given by this equation. The probability of starting in a particular state S1, which you typically don't control, that's determined by nature, times the product over all the time steps of the probability of taking an action, AT in state ST, times the probability of the world transitioning you to the next state ST plus 1. So if you multiply together all of these conditionals, you get a full joint distribution over capital T states and capital T actions. And for notational shorthand, we can denote the sequence of states and actions as a trajectory tau, and we can say that it's p theta tau. It depends on theta because the policy is inside this product. So that's the dependence on theta. All right, so this defines a full trajectory distribution. And now we can write down a reinforcement learning objective, sort of the simplest way of writing down the reinforcement learning objective in terms of this distribution, and that's given by this. So we'd like to find parameters theta that maximize the expectation under this trajectory distribution of the total reward of the trajectory. So our policy gives rise to trajectory distributions, which consist of states and actions. We can evaluate the rewards of those states and actions. We can sum them over all time, and it's that quantity that we'd like to maximize. And a lot of kind of very, very natural intuitive problems sort of boil down to this. So if you imagine, let's say your agent is playing basketball, and maybe its goal is to win the game, then at the end of that game, at time step capital T, it gets a reward of 1 if it wins and 0 if it loses. Everything else has 0 rewards, and that's what it's trying to do. Or you can have a reward that's a lot more dense in time. So for example, in the car accident case, maybe you get a reward of -1 each time you get into a car accident, regardless of which time it is, and you'd like to minimize the number of car accidents. So there's a lot of flexibility in how you actually choose the reward to utilize this formalism. Okay, yes?
What does the subscript on the expectation mean?
So whenever you see, yeah, we'll see this notation a lot in these lectures. The subscript in the expectation tells you what the expectation is with respect to. So this is an expectation with respect to tau distributed according to p theta tau. And we'll see these come up a lot. Okay. So one of the things to note about this equation is that this thing right here is actually a Markov chain, but a Markov chain not with the original state space, but with the augmented state space that consists of the state and the action. Now this is a little subtle, so let me draw the picture to try to illustrate this. So this is our Markov decision process graphical model. The state depends on the previous action, the previous state. Now we have a policy in here which relates the state to the action, so that sort of completes the picture. And we can kind of redraw this graphical model like this. We can say that actually you have a state and an action at each time step, which forms this augmented state space, and you're transitioning between these. And that's now just a regular Markov chain. And the transition operator for that Markov chain, the probability of being in a particular state and action at t+1 given the state and action at time t, is just given by the product of the MDP transition operator and the policy. So if we know the policy, we can actually turn our MDP into just a Markov chain. And that's going to be useful for us because that will allow us to rewrite that objective as expectations with respect to states and actions, even in the case where the episodes are infinitely long. So let's get into that a little bit. But first, does it make sense to everybody why we can turn this into a Markov chain if we know the policy? If anyone has any questions about this, please raise your hand. Yes?
So this holds even when the action is chosen stochastically?
That's right, yeah. So and here, this is the probability of the action. So the probability of the action is given by the policy. So if the policy is fixed, then you get a Markov chain. Yes?
Could you clarify what we're taking the product over?
This is the product over time steps. So you multiply the probabilities of the actions and the transitions for all the time steps between the first and the last. OK. So let's work on this Markov chain a little bit to see if we can understand the reinforcement learning objective a little bit better. So this is the objective I had before. So it's the expectation or the trajectory distribution of the total reward of that trajectory. This is the picture of our Markov chain. And this is its transition operator. And what we can do is we can actually take this sum outside of the expectation, because expectations are linear. And inside of it, we'll have the reward that depends on state st and action at. And that means that we can change this expectation to only be an expectation over st and at, instead of over the whole trajectory. And this probability of st and at, this is the marginal distribution at time step t in this Markov chain. So this p theta st at, you obtain that just by marginalizing out the probability of being in a state and action in this Markov chain, which we can do because it's just a well-defined Markov chain with a well-defined transition operator that just happens to have both s's and a's inside of it. So this I will sometimes refer to as a state action marginal. OK, this is probably kind of obvious. We'll talk about something a little bit more non-obvious in the next slide. But for this thing, does anybody have any questions about the state action marginal? OK, good. So now, that by itself is not particularly maybe interesting, but it will allow us to reason about infinite horizon problems, which is actually going to be pretty important. So what if capital T goes to infinity? OK, so if capital T goes to infinity, the Markov chain formalism allows us to actually understand what's going to happen. Remember that the transitions are linear. So you can say that the vector of the next states and action probabilities is given by T times the current probabilities, where T is actually the transition operator for this augmented Markov chain, not for the original MDP. So this includes both the policy and the transition dynamics. And because it's linear, we can say that, well, the state and action probabilities at time t plus k is just the transition operator raised to the kth power times the current state and action probabilities. So we can actually push this arbitrarily far into the future just by raising the exponent on t. So then we can kind of ask this question, well, if we keep doing this, as little k goes to infinity, do we actually converge to a particular stationary distribution? And we can actually write this down. If we know that this is the equation we're going to have, a stationary distribution is one where when you apply t, you get the same distribution. So it's mu such that mu equals t times mu. That means that it's stationary. That means it's not changing anymore. And we can do a little bit of algebra. We can basically subtract mu from the left side, and we can say if this is true, that means this is true, which means t minus identity times mu equals 0. And that's just an eigenvalue problem. So that this is true if mu is an eigenvector of t with eigenvalue of 1. And if t is a stochastic matrix under some regularity conditions, you can show that mu does exist. I won't go into the particular details of this, but under some regularity conditions, this does hold, which means that you can actually find a distribution over states and actions that this thing will converge to. Once you fall into the stationary distribution, because of this equation, every step after that, you'll stay in the stationary distribution because you'll just transition right back to it again. So mu is the stationary distribution. I can write out like this. I can write it as p theta s comma a, where I've removed the subscript t to indicate that this is the stationary distribution. And this we can now use to reason about what happens in the infinite horizon case. So as t goes to infinity, OK, one thing we want to do is we want to put a 1 over t in front of this thing because if we have infinitely many time steps and the rewards are maybe positive, that sum might actually be infinite. But that's easy to fix. We'll just say, let's go to average reward. Just divide by capital T. And then we'll take the limit of this as capital T goes to infinity. And the intuition here is that in the limit as capital T goes to infinity, if your Markov chain eventually falls into the stationary distribution and then stays there for an infinitely long time, that sum is entirely dominated by the expectation under the stationary distribution. So if you fall into the stationary distribution after 5 million steps, because your lifetime is infinite, you'll have so many steps after that that first 5 million basically doesn't matter. So that means that you can that in the limit as capital T goes to infinity, that objective is just equal to the expectation under the stationary distribution. So this is how we can analyze infinite horizon MDPs, and that's the objective. Does anybody have any questions about this? Yes?
Are you always able to write policy as a matrix in general?
So in general, no. So if your policy is operating on, say, continuous states and actions, or maybe they're discrete states and actions, but they're just so large that you can't write out the matrix in a computer, you might not be able to. But mathematically, this operator always exists. So even if the state is continuous, it's just an infinitely large operator. You might not be able to compute it, but it exists.
So you can't actually solve for the eigenvector, but you can simulate it or something.
That's right. So in practice, very few of the reinforcement learning algorithms actually attempt to compute mu. So dynamic programming algorithms will often try to do this.
Right.
But reinforcement learning algorithms rarely actually operate on these things. But it's good to know that they exist.
Right.
There was a question back there?
What would be like an intuitive explanation of what a stationary distribution was for like a certain reinforcement learning problem?
The intuition is something like this, that it's not that you fall into a particular state, it's that you fall into a particular distribution. So if you go on for long enough, eventually you basically forget where you started. So if your car is driving around on the road in San Francisco, if it's been driving around for long enough, its probability of being in any of the places that it might be is basically about equal because it doesn't depend on where it started. So that's all it means. It does not mean that you fall into a particular state. It's specifically a particular distribution. And that distribution might be very high entropy. Yes?
It's still an argmax, right? Or
Yeah. So there should be like kind of parentheses around this thing. Yeah. Was there another question back there? Yes?
So T is not known in applications, I guess, right?
Capital T?
Yeah.
Typically, we do know capital T. So this is part of how we define the problem. We might either say that our problem is episodic, which means that we have a finite capital T that we know. We might say that our problem is infinite horizon, which means that capital T is infinity. And then a special case of this is sometimes we might say we have an infinite horizon first exit problem, which means that the world does end at some point when you achieve your objective, but not after a particular time. It's when you reach a particular state. Yes?
So aren't we leaving a lot of information on the table if we kind of know the policy, but then we're just forcing it into this massive linear relationship between ST, AT, and ST plus 1 and AT plus 1?
Yeah, so just to be clear, this is just a mathematical formula to analyze the objective. We don't ever actually do this in practical algorithms. So we'll talk about some practical algorithms later on, but the only purpose of introducing all this stuff is so that we could write that equation up there, so that we could define the objective. All right, let's continue. So now we have two objectives that we've been able to derive. We have a reinforcement learning objective for the infinite horizon case, defined in terms of the stationary distribution of the corresponding Markov chain. And we have the simpler objective for the finite horizon case defined as the sum of the expectations under the state action marginals. So now, at least we know what it is that we're trying to accomplish. We're trying to maximize those things. One important thing to note about these objectives, and RL in general, is that we almost always, in reinforcement learning, care about expectations, not individual values. And this becomes quite important in some situations, because expectations do some funny things. Like, let's say that you're driving this car on the cliff, and your reward is +1 if you're on the road, and it's -1 if you fall off the cliff. So falling off the cliff is like a very discrete event. It's very discontinuous. You don't come back from it, you just fall off, and then you're gone. So the reward function is not smooth in S. Like maybe the state of the car is continuous, the position, the velocity, but the reward function is this very abrupt cliff. Like as soon as, like literally a cliff, like as soon as you go off of it, you're at -1. And let's say that if we like horribly abstract away the dynamics of a system, let's just say there's some probability psi that's your probability of falling off the cliff. Then the expectation of the reward under the state distribution with this probability psi, even though the reward itself is discontinuous, the expectation is actually smooth in psi. So you can think of psi as being, like if you drive the car 1,000,000 times, psi is the fraction of those trials on which you'll fall off the cliff. So even though the reward itself is discontinuous, as you continuously vary psi, the expectation does vary continuously. And this is very, very important because this is what allows us to use things like gradient-based algorithms with reinforcement learning to optimize non-smooth objectives. Non-smooth either due to non-smooth dynamics or due to non-smooth rewards or both. And this is very important, that we're almost always actually concerned with expectations. Does anyone have any questions about this? This is pretty important to understand. Yes?
Sorry, so if your like falling probability is not discrete, then do you like set a threshold at which psi is like the probability of falling below a threshold?
So psi is just a number between 0 and 1. It's just a probability of a discrete event. So that, my point is that if, like, you know, in practice, of course, you don't get to control psi. You control some complex policy that somehow indirectly leads to that. But the point is that in expectation, over an infinitely large number of trials, this discontinuous thing up here becomes smooth.
I'm sorry, I misphrased that. If your discrete event is not discrete, if you have numerous possible
Right.
actions.
Yeah. So if you have numerous possible actions, then it's even, and they're not discontinuous, then it's even easier. But the point is that even if things are discontinuous, in expectation, they can become smooth, and generally they do. Yes.
So can I intuitively understand this as like if you drive still on the road but really close to the cliff, then you don't want to be there because the expectation,
Right.
the probability of falling off.
Yeah, so that's one of the consequences of these things, is that in stochastic environments, and this is also why stochasticity is important for these kinds of control problems in stochastic environments, you will typically do things like avoid dangerous situations because there's some increased probability of an adverse outcome. Yes?
Yeah, it seems to me that introducing this psi probability actually just change the reward function, change from not smooth to smooth. Is that correct?
There's a distinction to be made here between objective and reward functions. So reward function has a very specific definition. A reward function is a function of state and action. The objective is the expectation of the reward function. So the objective is smooth, the reward is not. All right. So that's definitions and objectives. Now let's start talking a little bit about algorithms. And I won't cover any particular algorithm in detail today, so don't worry if you don't completely understand how the algorithm works, but I just want to give a little bit of an overview of the structure of the algorithms that we'll study in the next few weeks. So for pretty much all of the algorithms actually that we'll study, they're going to consist of 3 parts, although sometimes these parts are a little degenerate. They're going to have some part that generates samples. So a sample, when I say sample, what I mean is you run your policy in your real world or in your simulator, and you see what it does. So a sample is a sample of a trajectory. Sometimes in online algorithms, a sample is actually just a single transition, so like a really short trajectory. For episodic algorithms, it's typically an entire trajectory. Then almost all, actually all algorithms that we'll cover in this course, and in general almost all algorithms for RL, will have a stage where they fit a model or estimate a return. So this is sometimes referred to as a policy evaluation stage for policy learning algorithms, sometimes referred to as a model fitting stage for model-based RL algorithms, but it's a stage where you're not actually changing your behavior, but you're looking at your samples and trying to figure out what happened, either how good is your policy or how do the physics of the environment work. You're trying to analyze the results in some way. And then there's a third box which actually improves the policy. So pretty much all the algorithms will have these 3 stages, and for each one I'll try to point out what these stages are. So these stages, they might be sometimes very simple. So we'll learn about policy gradient algorithms where evaluating the policy just means take your sample and sum together its rewards. So it's just a summation operator, very trivial, all the way to like more complex things like Q-learning or model-based RL algorithms where you're actually fitting an entire neural network in that blue box, either to understand the expected reward of your policy or to understand the physics of the environment. So this box can be really, really simple, or it can be really complex. Improving the policy, again, for policy gradient algorithms that we'll study next week, improving the policy is just a gradient step. For things like Q-learning and value function learning algorithms, which we'll study the week after that, improving the policy just amounts to evaluating the action that maximizes the Q function. And then for model-based RL algorithms, this might be something like optimizing your policy by backpropagating gradients through your model. So there are different choices for this, some of which range from things that actually optimize a neural net, or things that just take a single gradient step. So again, both boxes can be either really simple or really complex, but they're always there. Which parts are cheap or expensive? Again, depends on the particulars of your algorithm and also on the particulars of your problem. So if you're running your algorithm on a real robot or a real car or whatever, like a real power grid or something, some kind of real physical system, then generating the samples runs in real time until we invent time travel. Although if you're lucky enough to have multiple physical systems, maybe you can parallelize that. If you're generating samples with the Mujoko simulator, well, for your homework, for example, maybe this is running at like 10,000x real time. So depending on the particulars of your problem, whether you're using simulation or not, this box can either be the main limiting factor that limits your performance, or it might be completely trivial. Fitting a model and estimating the return, again, it might be as simple as just adding together a bunch of values, or as complex as fitting a complicated neural network. So that might be either really simple or really complex. And again, improving the policy can be as simple as maximizing some value of a function approximation you've already fitted, all the way to backpropagating into a policy in model-based RL. OK, so let's study a really, really simple toy RL algorithm. This is not actually a very good idea to do for a practical reinforcement learning example, but I'm going to use this to illustrate that structure with the 3 boxes. So the example here is this is actually a model-based RL example. I've kind of nicknamed it RL by backprop. So the idea here is that you have fully deterministic environments, and you have a policy, which is a neural net that looks at the state and gives you an action, and a neural net that looks at the state and action and gives you the next state. So this is sort of reinforcement learning stuffed into a recurrent neural network. And the way you optimize your policy is just by backpropagating the gradient of the reward. OK, so this is just like exactly the same way that you train a neural net, RL by backprop. OK, and this is our picture. This is you can generate your samples, fit your model, and estimate your return, and then improve the policy. So one of the things you need to do in order to use this little toy algorithm is collect the data. So collecting the data, obviously, is the orange box. That's your sample generation. Then you have to update this model F. So you need to make sure that this thing actually models the transitions in the real world. So this is the green box, right? Fit a model, estimate the return. And then you have to do a forward pass in this computation graph, in this network. Does anybody have any guess where the forward pass, which box the forward pass fits into? Raise your hand if you think it fits into the green box. Raise your hand if you think it fits into the blue box. OK, so I guess this analogy sort of confused everybody. So the forward pass is what you use to evaluate the R's, right? So in this computation graph, you run the forward pass in your neural net, and you get values for R's. So that's going to tell you, yes?
I don't quite understand what the return means in this, or you say estimate the return.
Sorry, return is a synonym for objective value.
Okay.
Yeah. Yes?
Is running the policy not a forward pass?
So forward pass in this computation graph. Yeah. So the forward pass in this computation graph amounts to sort of running the policy through whatever you have in this box here. So this is going to give you values for the R's. And because it gives you values for the R's, that's what basically tells you what your return is. So if you want to know what your overall objective value is, if your objective value is the sum of the R's, you just run this thing forward and that gives you the R's. Yes?
I'm a little bit confused about the green box. So when you say fit a model, does it mean fit a model for the agent, or does it mean fit a model for the world?
It depends on your algorithm. So not all algorithms will try to fit a model for the world. The main distinction between this and this is that the policy doesn't change here. So no modification is made to your actual behavior, whereas this actually modifies your behavior. So in the case of this little toy algorithm, anything that involves evaluating your rewards through, in this case, using a forward pass or updating the model, which is this box right here, that's right there. And then the only thing that actually modifies your policy is when you then compute the gradients with backprop and take a gradient step. So that's the blue box. So this is kind of by analogy to like neural net training. If you're training a neural net, you have your forward pass and you have your backward pass. Yes?
Why do we need the duplicate to that?
Sorry?
Why do we need the duplicate to that? Like a double R, double A, I, and double S, I.
Oh, sorry. This should be +1. This should be +2. Yeah, that's just a typo. Okay. So this is yes.
Do you not update the model with model F with gradients, or?
Yes, but when you update the model, you don't. That's not changing your behavior, right? So you're only acting according to this in the real world.
Yeah.
So whether your algorithm is model-based or model-free, anything that sort of doesn't change your policy, we put in here. And this distinction is going to become a lot more important later on when we talk about the model-free algorithms. Yes, there's a question back there.
So in this case, you have something kind of like where the network is used to like perform Q learning, but improving the policy is just like taking the cues from the network and then actually like tabulating them.
That's right. So when we talk about Q learning afterwards, for Q learning, indeed, this stage is the one where you basically use your best Q function to improve the policy, and actually learning a Q function would be up here. And that we'll talk about, I think, the week after next. There was a question here?
So model F is predicting the next state.
Yeah.
Okay, and then you're updating that model, but you're also updating the model that is predicting the action, which is the policy, or you're not updating the policy?
So the policy is updated last, because yeah, because you'd have to update it with a different objective. The policy is updated to increase the reward. The model is updated to mimic the real world. Yeah. So this is sort of the sketch of a basic model-based RL algorithm in this case. And the reason I wanted to go through model-based RL is because we can deal with it without having to worry about gradients of expectations or anything like that. So this is just sort of the same tools that we use to train regular neural nets. Okay, this is not actually like a very good RL algorithm the way I described it, because it only handles deterministic dynamics, it only handles deterministic policies, only continuous states and actions, and so on. So in general, this is not something you'd actually want to do as described, although later on in the class we will talk about model-based RL algorithms that do modify this framework a little bit to make it actually usable for practical reinforcement learning problems. Okay. So how can we work with stochastic systems? So with stochastic systems, everything is in terms of expectations. And one of the tools that's really useful for us to understand for this is conditional expectations. So let's recall this objective, the finite horizon expected reward, the sum over time steps of the expectation of the reward under the state action marginal at time step t. One of the ways we can rewrite this, this way of writing it, it's a little bit sloppy because it's not clear kind of where, what is dependent on what. We can write it out a little more formally like this. We can say, on the very outside, we have an expectation of the first state. And the first state is distributed according to the initial state distribution. Inside that expectation, we have an expectation of the first action, which is distributed according to the policy. And here now we can write the first reward. So this is a conditional expectation conditional on the first state, right? And then what do we add to it? Well, we add to it the second reward and the third reward and so on. So the second one is an expectation with respect to the second state, which is distributed according to the dynamics, and now conditional on the first state in action. And in here, it's an expectation with respect to the second action, distributed again according to the policy, of the reward plus the expectation of the third state, and so on and so on. So if we were to actually write this all out, and keep track of the conditionals that are actually influencing this, we'd have all these nested conditional expectations. Does anyone have any questions about this way of writing the objective? Okay. So now let's imagine for a moment that all we want to do is figure out a really good action for the first time step. If we know this expectation, if we know all the stuff in here, then it's very easy for us to choose the first action, because all this stuff, it depends on the first action, and nothing outside of it depends on the first action. So if we just had some oracle that told us exactly what was in here, let's call that oracle QS1, A1, then we could very easily choose the first action. We just choose the first action to be whatever this oracle tells us gives us the biggest expected reward. So very often when we work with reinforcement learning algorithms, we'll define functions like this Q here that that sort of contain inside of them expectations of all the future rewards. So these are conditional expectations, conditioned on a particular state and action. So QS1, A1, in this case, is the conditional expectation of all of your rewards in the future, conditioned on being in state S1 and taking action A1. It just so happens that if you know QS1, A1, it's very easy to choose the first action, because you could just choose the one that makes that thing big. So you can rewrite your full objective like this now. I've just taken this thing and substituted QS1, A1. And now if this is your objective, well, it's easy to modify the policy at the first time step, because if you know this thing, you just take the one that maximizes the Q value at the first step. And you can do this at the second step and the third step and so on and so on. So I haven't told you yet how to actually do this, but the point of this slide is that it's often very, very convenient if you know these conditional expectations, because then you can use them to actually improve your policy. So this is a definition that's going to be very important in many of the algorithms that we'll cover. So the first thing that we want to define is what's called the Q function. And the Q function, in general, is defined as a function of the state and action at time step t. And it gives us the conditional expectation of the total reward from this time step until the end, if we start in state st and take action at. A second definition that's very important to know about is the value function. And the value function, very simple. It's just the expectation of the Q function with respect to your policy. So if you start in state t, it's the total reward that you'll get if you then follow the policy. And the Q function, if you start in state st and take action at, what will you get from your policy? There's a question back there?
I guess I thought Q function is for a particular step, but it depends on the policy because it gives you the reward from it.
Yes, so this is what I was actually just about to say, is that there's a little superscript pi up here. So this is specifically the Q function for a policy pi, because of course your future rewards depend on what you're actually going to do in the future. And the same for the value function. So these depend on some policy pi. So the value function is the expected reward if you start in state S, and it can also equivalently be written out as the expectation of the Q function under the policy. So that can be quite convenient sometimes. And from this, we can actually see that the expectation of the value function of the first state is actually our reinforcement learning objective, because the expectation of the value function of the first step is this thing, which is the total reward that we'll get starting from states sampled from the initial state distribution. So we can equivalently rewrite the entire RL objective like this. OK, so a quick preview of why Q functions and value functions are valuable. There are a couple of very convenient things we can do if we know Q functions and value functions, or if we fit them, or if we estimate them. So one idea, if we have a policy pi and we know its Q function, then it's very easy to improve pi. So one of the ways we can improve pi is we can write down a new policy, pi prime, that basically assigns a probability of 1 to an action if it's the argmax of the Q function, and a probability of 0 otherwise. And we know that this policy will actually be at least as good as the policy pi, because it's taking the actions that maximize the future returns under that policy. So that's sort of one idea that we might have, and we'll revisit this idea later. So this policy is at least as good as pi, and probably better in practice. And it actually doesn't matter what pi is. A second idea, we can compute gradients to increase the probability of good actions A. So if we want to have a neural net policy, and we know the Q function, we can use it to compute gradients. So in particular, if the Q value of an action is better than the value at that state, then that action is sort of better than average, right? Because we've defined the Q function, or this is actually backwards. This should be V pi is equal to the expectation of Q pi. So the value function is the expectation of the Q function. So that means that if the Q value of a particular action is bigger than the value at that state, then it's better than average. So that means that we can modify our policy to increase the probability of actions that are better than average, and that'll get us a better policy. And we can actually use this to compute gradients. So that's another thing we can do with value functions and Q functions. So these ideas are very important to RL, and we'll revisit them actually again and again as we talk about policy gradients, actor-critic algorithms, and Q-learning algorithms. If you know value functions and Q functions, they tell you a lot about how to improve your policy, because they basically compress all the future rewards into a function of the current state or the current state in action. OK, let's review. So we talked about some definitions. We talked about Markov chains, Markov decision processes. We talked about the RL objective, which is expressed in terms of the expected reward. We talked about how we can evaluate expected reward for infinite horizon problems. We talked about the structure of RL algorithms. There's a sample generation phase, a model fitting or return estimation phase, and a policy improvement phase. And we talked about value functions and Q functions. So does anybody have any questions about any of the things here? Yes, question back there.
Here we involve the model and the policy. Are they the same thing or different?
Generally not. So there's a little bit of kind of terminology confusion, because in deep learning we often use the word model to be synonymous with neural network. And if your policy is a neural network, then it's also a model. Usually when I say the model in this course, I mean a predictive model of some sort, which is going to be either a model of the transition dynamics or a value function or Q function. And I'll try to check myself and make sure that I always call policies policies rather than models. Yes?
Could you go back 2 slides
to the value function slide?
Yeah, the value.
OK. This one?
Yeah. So like the last line. So isn't that like overcounting the metric that you actually want? Isn't it actually expectation over the density function of the immediate reward you get at each state?
So this is the expectation of the initial state distribution.
Yeah.
So if the value function is defined as the sum of the expected rewards that you'll get starting in a particular state, and then you average this over all the initial states,
okay, so
then you get exactly the sum of rewards overall. Yeah, that's right. Yes?
I'm also wondering what exactly is the notation like. So you have like E probability distribution of some function given a random variable.
Mm-hmm.
And is that common notation? Or?
Yeah, it's pretty common.
So what is that exact? So is it like the expectation? So pi theta gives a distribution over all of the.
Pi theta gives a distribution. Well, yeah, there's a little bit of overloading here, because on the slide where I defined the objective, I actually kind of abused pi theta to mean both trajectory distributions and action distributions. So maybe don't worry too much about that one, because it's a little clumsy. Okay.
What does the tilde notation mean?
Tilde?
Yeah, I mean.
Where do you see a tilde?
In the subscript there is AI and tilde P.
Oh, A distributed according to. Okay, let's take a 2-minute break, and then we'll come back to the last portion of the lecture, which is going to involve some case studies and videos. Yep.
So in the capital tau, which was the transition matrix, we made some stationary, like we said, stationary under some assumptions. I was gonna ask about a case. So you gave the example of like driving around in San Francisco, but San Francisco is like a limited area. So there's,
Yeah. So the regularity assumptions, there's a few of them. I don't remember all of them off the top of my head, but some of the ones that matter, for example, are whether your system is ergodic. So can you come back to a particular place? So if you drive around San Francisco, but there's a one-way bridge or something, and you can never come back from that, then things might be a little different.
Yeah, I was thinking of universe, like say you just go farther away, like you just there's infinitely many places.
Yeah, well, and in fact, some of the standard regularity assumptions are actually often not reasonable in real-world problems. So in practice, that analysis sort of only gets you so far, but it's useful for at least writing down a definition.
Okay, so like we don't really rely on those like regularity assumptions aren't necessarily need to be satisfied for us to be able to use.
Well, this is sort of the troublesome aspect of some of the algorithms that we'll learn about is that oftentimes, and this is I think going to be a theme, is that the kind of regularity assumptions that do guarantee convergence are not ones that actually ever hold in practice.
I see.
And we'll see this again and again with a lot of the model-free algorithms that we'll study.
Thank you.
I have a question about Markov's definition.
Okay.
So, isn't that like from the context of an MDP in isn't Markov is actually like if you have sufficient information to like act optimally on the particular based on that?
Well, so the Markov property doesn't actually have anything to do with being able to act optimally. It just says, is the future independent of the past?
But that's like the Markov chain version of
that's the definition of the Markov property.
But in RL, it's like even if you like don't receive any information from the environment, it would satisfy the Markov chain because at every state you won't receive any information.
So you're talking about the partially observed history thing.
Not necessarily history. It could even be like noisy observations. Or like you don't get everything. For example, in Muchoki, you don't get all the.
So, in general, there is a difference between the partially observed formulation and the fully observed formulation because optimal strategies under partial observability will include behaviors that attempt to explicitly gather information. So, in that sense, it is actually important to consider the distinction. There are a few shortcuts you can make, like if you actually have a policy that depends on the entire history, you can show that if that policy is sort of infinitely expressive, it's at least as good as any kind of state estimation method. But in practice, sometimes it's convenient to consider one, and sometimes it's convenient to consider the other.
Yeah, but that still need not satisfy the Markov chain, but it would still be like Markov in the context of being able to do that. Like for example, you may not. Like,
well, no. If you have the full history, the augmented state defined by the full history is Markovian, because because there's nothing to be independent of. Like if you have the full history, there is no previous thing.
History of the observations or history of
observations.
That need not still give you the internal state. Like for example,
it doesn't necessarily give you the internal state, but it satisfies the Markov property in that it's independent of the past. So if you know 01 and 02, then you don't, like if you have both of those things, then you don't need to know just 01. So it's sort of trivially Markovian just by by construction. I think I should actually start the next portion. Okay, we're going to continue. All right. So in the last part of this lecture, I'll briefly summarize a few different types of RL algorithms and show some results from recent papers that actually use some of these algorithms. And then we'll cover the algorithms in detail in subsequent lectures in the course, and this is sort of just meant to give you the overview. So at a very high level, we'll cover a few classes of algorithms, and this is roughly in the order that I think we'll do them in this course. So we'll talk about policy gradients. Policy gradient methods directly write down this objective, the expected reward objective, and then they compute its gradient with respect to the parameters of a policy. And we'll talk about how to do that next week. Value-based methods attempt to estimate the value function or Q function of the optimal policy. So the sort of pure value-based methods don't actually explicitly represent the policy at all. They just try to figure out what is the value function or Q function and then act by maximizing the Q function. Actor-critic methods do a little bit of both. So actor-critic methods will estimate a value function or Q function and then use it to compute gradients for a policy. So you can view actor-critic methods as being basically policy gradient methods plus value function estimation. And then model-based methods, which are a little bit different from the rest, they're going to try to estimate the transition operator. They're going to basically estimate the physics of the world, and then they're going to do a number of possible things. They might, for example, just use that transition model for planning without any explicit policy, so then the only thing that you learn is the transition. Or they might use the transition function to improve the policy, to compute gradients. Or they might do something else. They might, for example, use it for dynamic programming, for simulating synthetic experience to give to a model-free learner, and so on. Okay, so these are broadly the four categories of methods that we'll learn about. So model-based RL algorithms, let's try to see how they fit into this picture. they're going to learn their transition operator up here, and then they're going to do something to improve the policy. And there are a number of possible options for this. So those options include just using the model to plan. So this is the kind of stuff that uses traditional optimal control algorithms or discrete planning algorithms, and we'll learn about a few methods for doing that. So trajectory optimization or optimal control, primarily in the continuous case, which is essentially backpropagation to optimize the actions, or discrete planning in discrete action spaces. So Monte Carlo tree search is an algorithm some of you might have heard about that does something like this, and we'll learn about that as well. Another thing you can do is if you learn the model, you can backpropagate gradients into the policy. So this is a little bit like that little toy RL by backprop example that I showed. It requires some tricks to make it actually work in practice. And then you can also use the model to learn value functions and Q functions. So you can do this with dynamic programming if you're lucky enough to have small discrete environments. And you can also do this by using your model to generate essentially synthetic experience and then give that to a model-free learner. And this is a popular class of algorithms that do this is called DYNA. So there's basically, there are different ways to use a model in a model-based RL algorithm, and we'll learn about a few of those options. Value function-based algorithms. Value function-based algorithms fit a value function or Q function. And pure value function-based algorithms don't actually have an explicit policy. So in this box where they improve the policy, they just set the policy to be some function of the Q function or value function. A very common one is just say, take the action that maximizes the Q function. And we'll learn about those as well. Direct policy gradient methods. If they don't use a value function or Q function estimator, then all they do in the green box is they just sum together the rewards. So they improve the policy with a gradient operator, hence the name. And then up here, they typically just evaluate the return by summing together the rewards that were observed. So this is very, very simple. And then a lot of the magic goes into how you compute this gradient. And then actor-critic algorithms do a little bit of both. So they fit, so they take an update on the policy using policy gradient style methods, but then they get a better policy gradient by actually fitting a value function or Q function, and then using that to estimate the returns instead of simply summing together the rewards that were observed. And we'll study why this might actually be desirable in some cases rather than directly using the rewards that you observe in your samples. So these are, very broadly speaking, the different categories of reinforcement learning methods. And let's now talk a little bit about some of the trade-offs that we might consider. So why do we have so many reinforcement learning algorithms? We'll learn about all of them, but I think it's a good idea to get some initial preview for why we actually need so many and why we need to bother learning about all of them. So the issue is that, in contrast to supervised learning, where, if you want to train a neural network with supervised learning, you pretty much use some flavor of gradient descent, and while you might argue about whether SGD with momentum is better or worse than using Atom, in the end, they all look extremely similar. In reinforcement learning, this is not really the case. In reinforcement learning, different algorithms actually have very different trade-offs. We don't have a single algorithm that performs best in all cases, partly because maybe we haven't quite figured it out yet. So it's important for us to study different kinds of algorithms and understand their trade-offs. So what are the kind of trade-offs that we have to consider? One of the big ones is sample efficiency. And sample efficiency refers to how many samples you have to generate in this orange box before you get a good policy. Sometimes we want to consider stability and ease of use. So this refers to how difficult is it to choose the hyperparameters for the algorithm, the learning rates, the exploration parameters, and so on, to get it to actually work. And this is very easy for some methods and extremely difficult for others. And the different algorithms will sometimes have slightly different assumptions. For example, some algorithms will assume stochastic dynamics and stochastic policies. Some would operate better on deterministic dynamics or maybe deterministic policies. Some of them will work better in continuous settings versus discrete. Some of them prefer episodic settings rather than infinite horizons. So episodic means that capital T is finite. Infinite horizon means that it's infinite. And then different things are easy or hard in different settings. So even if your problem fits into the assumptions of a particular algorithm, maybe the particulars of your problem will influence which method works better or worse. So is it easier to represent the policy, or is it easier to represent the transition function? That depends on the particulars of your problem. Maybe it's easier to represent the value function. So then that, again, will inform your choice of method. So let's talk a little bit about sample efficiency first. So sample efficiency means how many samples do we need to get a good policy? How many times do we have to attempt running our policy in our simulator or in the real world before it gets it plateaus and reaches its peak level of proficiency. So that's all about this thing. One of the most important questions in understanding how efficient an algorithm is to understand whether it is off policy. So off policy means that the algorithm can improve the policy without generating new samples from that policy. Meaning, can you use historical data that you generated with other policies to make the current policy better? On policy means that each time the policy is changed, even if it's changed a little bit, you need to generate new samples. So there's a big distinction between these. And it's a hard distinction. So if the policy's changed even a little bit, an on-policy method needs completely new data. And that can be a big deal if you're changing your policy with gradient methods, because a gradient might change it only a tiny bit. Yes?
Can you give some examples on off-policy and on-policy?
Yeah, I'll do that in a second. Yeah. OK, so if you take just one gradient step, that actually will change your policy. So if you have a big neural network and the gradient step only changes it a tiny bit, you might end up generating many, many samples. OK, so let's sort of draw a little map. And this map is very approximate because the efficiency of different algorithms is going to depend very strongly on the particular problem you're trying to solve, the particular reward function, and so on. But at a very high level, we can draw a little bit of a map to kind of map out the space of sample efficiency for different algorithms. And we're going to put this little barrier on that map. Everything to the right of this is going to be on policy, and everything to the left is going to be off policy. So a very simple class of on-policy algorithms are sometimes referred to as evolutionary or gradient-free algorithms. So these are algorithms that actually don't even use the gradient of the neural network. They don't have any step that performs backpropagation. They just treat the parameters as sort of the parameters of some black box, potentially non-differentiable function, and operate directly on the parameters. These methods tend to require the most samples because they're not getting the benefit of the gradient. By the way, just as a quick note, I'll talk about afterwards why you might actually want a less efficient algorithm in some cases. So less efficient is not synonymous with bad. It just means less efficient. On-policy policy gradient algorithms are a little bit more efficient. So they're still on policy, meaning that every time the policy changes even a little bit, they need new samples, but they would still use the derivative of the neural network. So they tend to be a little more efficient because they have that gradient information. Actor-critic style methods can actually fall on either side of this divide. So there are actor-critic methods that are on policy and actor-critic methods that are off policy. Off-policy Q-function learning methods. So oftentimes, if you're learning a Q function, you can actually do it entirely off-policy. These tend to be a bit more efficient. And then model-based RL algorithms are a little bit more efficient even than that. And shallow RL methods, methods that don't fit neural nets, that use, for example, very efficient Bayesian function approximators, tend to be even more efficient, but typically at the cost of introducing additional assumptions or restricting the class of problems that they can succeed on. So that's kind of the high-level map of sample efficieny. So then one might ask, well, why would we use a less efficient algorithm? Like, why do we even need all this stuff over here? There are a few answers to that that have to do with all the other trade-offs. But one of the things that's perhaps most relevant for this slide is that wall clock time is not the same as efficiency. So efficiency matters if you don't want to generate very many samples. But that's not always your constraint. So if you have a really fast simulator, maybe you don't really care about this at all. What you really care about is maybe the total wall clock time. How long does it take you to optimize your policy, which includes simulation time and neural network optimization time. And it actually just so happens that wall clock time looks almost like the opposite of this picture. So the reason that we might want gradient-free or evolutionary algorithms over here is because in some cases with enough parallelism, they're actually the fastest in terms of wall clock time. Policy gradient algorithms, even though they're on policy, are also often very easy to parallelize and often quite quick in terms of raw wall clock time if your simulation is very, very cheap. In contrast, model-based RL algorithms, even though they make the most of the data that's available, they actually tend to be very slow in terms of wall clock time because you're fitting a lot of different neural network models. Maybe you'll fit a transition model, and you'll fit a policy, and then you have to backpropagate through a long temporal sequence. So these things might actually be more expensive computationally. Does anybody have any questions about this? OK. Did you have a question?
I guess you'd probably go over this, but is there a way to know, how do you determine, just looking at a problem, looking at a set, like an algorithm, if it's on policy or off policy, I guess?
Yeah. So there's a very simple test. if you change the policy even a little bit, do you need to generate new samples?
I mean, that's the question, like how do you know that?
So you know that from the derivation of the algorithm. So usually when we derive an algorithm, we derive it in a way that it's optimizing some objective, and in the process of doing that, we can typically figure it out. Yeah.
Okay, that makes sense.
Yes?
What exactly is model-based shallow RL?
Model-based RL that doesn't use a high-dimensional expressive function approximator, like for the model. And we'll see some examples of that later in the course. All right, another dimension for where we might consider trade-offs: stability and ease of use. So if we're concerned about stability and ease of use, that means that we're asking a number of questions. One question that we want to ask: does the algorithm converge? If it converges, what does it converge to? Not always an easy thing to answer, by the way. And does it converge every time? So is the convergence an empirical result, meaning like, I ran it 5 times and it seems to converge, or is it a theoretical result, meaning if I run it 5 million times, it'll converge every single time? And why is any of this even a question? You'd think that if we have supervised learning algorithms for training giant networks on ImageNet, and those algorithms, at least with the modern techniques, they very, very frequently and almost always converge. Why are we even asking this? Well, it turns out that supervised learning methods for deep networks, they're almost always some kind of gradient descent. And gradient descent is actually relatively straightforward to analyze, reasonably well understood and very heavily studied, and we have good ways to get things to converge that way. Reinforcement learning is actually often not gradient descent. So we'll learn about reinforcement learning algorithms that are gradient descent, and coincidentally, those tend to be the most stable and the most easy to use. But many of the more efficient reinforcement learning algorithms are not gradient descent, meaning that they are not computing and taking steps on the gradient of the objective that you want, which is the expected reward. Instead, they're doing something else that under certain conditions can be shown to converge to the optimum of the expected reward. And those conditions sometimes do or do not hold in practice. So, for example, Q-learning is an instance of what's called fixed point iteration, meaning that it is not the gradient of the expected reward, it's something else that, under certain conditions, can be shown to converge to the optimum of the expected reward. And those conditions are often not the ones that hold in practice. Model-based RL, when you optimize the transition model, it's not actually optimized with respect to expected reward, because that doesn't make sense. You optimize it to accurately fit the physics of the real world, and that has some really complex implications on the performance of the corresponding policy. Policy gradient actually is gradient descent, and therefore actually is often easier to use, but it's also one of the least efficient methods in terms of sample complexity. So these are trade-offs that we have to keep in mind, and oftentimes we'll see that more efficient methods, they're more efficient because they do something clever, but because they do something clever, they're a little harder to use and a little bit less stable. So some kind of examples of this. Value function fitting, typically what you optimize when you fit value functions is how well do you approximate the expected rewards, but approximating expected rewards accurately is not the same as having a good policy. So it's not the same as actually maximizing the expected reward, it's minimizing the error of your predictions. So at worst, this actually doesn't optimize anything as far as your expected reward, although under some assumptions it does. But the bad news is that many of the popular deep RL value fitting algorithms are not actually guaranteed to converge to anything in the case where the value function is fitted with a nonlinear function approximator like a neural network. Model-based RL, again, your model typically minimizes some error of fit, basically some accuracy in predicting the future. Predicting the future is a well-defined prediction problem. Typically, it reduces to supervised learning, so that will converge. But remember that second question, what will it converge to? Well, it will converge to an accurate model, which doesn't necessarily mean that you'll have a better policy. So those are some of the issues. Policy gradient, the only one that actually performs gradient ascent, actually, if you have a reward on the true objective, but again, has some other trade-offs. Another thing that we might want to consider as far as trade-offs, assumptions. So there are a few common assumptions that some algorithms make and not others that may be a little limiting. Sometimes they're very limiting, sometimes not so much, so that depends entirely on your problem. So some algorithms, for example, will assume full observability, which means that the state and the observation are one and the same. And the car never drives in front of the cheetah and causes you not to see it. So this is generally the assumption for value function fitting methods. And there are ways to get around it and still fit value function when you have observations. But the basic version of these algorithms has that assumption. You can mitigate it by adding recurrence, essentially considering your history, just like we talked about on Monday's lecture, and we'll discuss that a little bit too. Another common assumption that some algorithms make is episodic learning, which is basically to say that capital T is less than infinity. So episodic learning sometimes makes sense. This is a robot that's doing some episodic learning, so it keeps trying to put the Lego block in that spot, and an episode is of well-defined length. This is often assumed by pure policy gradient methods that don't use a value function approximator, and it's also assumed by some model-based RL methods. Another assumption that some methods make is continuity or smoothness. So it turns out that if you know your actions are continuous, there are a few tricks you can do for both model-based and model-free RL. If you know that your dynamics are smooth, there are some other tricks you can do. Those are a bit more common for what I called shallow model-based RL previously. So this is used in some value function learning methods and quite common in many model-based RL methods. So these are just a few examples of assumptions, and when we talk about individual algorithms, we'll discuss their assumptions. But that's something to keep in mind as far as trade-offs. Does your problem setting actually satisfy the assumptions to allow you to use a particular algorithm or not? Okay, so let's talk about some specific examples of algorithms. Some of you might have heard of some of these, so I just wanted to mention them in case you're wondering. If you haven't heard of them, don't worry about it. We'll talk about it in the class. So some examples of value function fitting methods. If you've heard about DQN or Q-learning, that's a value function fitting method. Temporal difference learning, and fitted value iteration. So these are some examples of algorithms that you might have heard about. Policy gradient methods. If you've heard about reinforce, reinforce is a very classic policy gradient method that we'll study next week. Natural policy gradient is a more advanced policy gradient method that we'll study later in the course, and trust region policy optimization as well. Actor-critic algorithms. If you've heard about asynchronous advantage actor-critic, or A3C, that's an actor-critic algorithm. Model-based RL algorithms, things like DYNA or DYNA-Q, those are model-based RL, as well as guided policy search. So if you've heard of any of these, this is to put them into the right slot for you based on today's lecture, and we'll study these later on in the course. So if you haven't heard of them, don't worry. Okay, so let's look at a few examples. This is a video of a value-based reinforcement learning algorithm. This is from the DQN paper. So this is an example of a convolutional neural network that is trained to estimate the Q function, which, as you remember, is the expected reward if you take a particular action in a particular state. So the agent here is playing these video games. It's not explicitly learning the policy, it's learning the Q function, which means it's learning to predict the expected future rewards and then taking the action for which it predicts it'll get the highest future reward. So this is Q learning with convolutional neural networks, and this we'll study in a few weeks. Here's an example of a model-based RL algorithm. So this is using guided policy search to do vision-based robotic manipulation. So this algorithm combines learning a policy with fitting local models of the dynamics, and we'll study this later in the course as well to eventually learn policies from pixels for some basic robotic manipulation tasks. Here's a video of a policy gradient algorithm. So, this is actually an algorithm that combines a value function estimation and policy gradient, so it's technically actually actor-critic. And here this little humanoid is learning to run, and you can see the learning process at first falls a little bit and gets the frowny face, but once it has enough iterations, it can figure out how to actually run for increasingly longer and longer periods of time. So this is using a policy gradient method called trust region policy optimization and a value function estimation method called generalized advantage estimation that we'll learn about later in the course. All right, so next week we'll talk about our first model-free RL algorithm. So in week 3 we'll talk about policy gradient algorithms, and you'll need these for homework 2, and then we'll cover the other algorithms I've discussed. So yeah, see you all next time.